independent practice, just part 2. If you look at your answers there, that is what they should look like. I think for the most part we were wrapping up yesterday's lesson and finishing these 3 up. So I just wanted you to make sure you have those answers in your notes. Okay, with that, were there any questions on A, B, or C in independent guided practice number 2? Comments, concerns? Okay. Now your answers for independent guided practice number 3. Part A, your answer there is 98. All I did was I evaluated f of 5 and I got 7, and then I just evaluated g at 7, so g of 7 ended up being 98. For part B, I got 142 as my answer. I evaluated g of 5 and got 50, and then I evaluated f at 50, and that's how I got 142. And then for part C, and I was kind of hearing the same from you folks, I evaluated f of 5 and got 7, and then I evaluated f at 7 and got 13. Okay, so were there any questions about that? Okay, I did want to just briefly talk about, I'm trying to think which way I want to go. I think I'm going to talk about your homework that I just passed back when I go to talk about your homework for tonight a little bit more. So don't put that homework assignment that you just got back too far away. I actually have 3 things that I need to point out to you folks before, I completely hand over that homework assignment. Okay, so for today, to be very, very clear, and I heard the question when you came in the room is, how do I understand or get the domain for our composite functions? And I have to call your attention to maybe a piece of the notes that you watched in last night's video, or maybe you watched it the night before, but I'm going to show you where you would look to find a little bit of official guidance on that. What's important to consider when determining the domain of your composite functions is actually the domain of the original functions themselves. So if we're making a composite function h, and you want to determine its domain, you need to take into consideration the domains of both f and g. Okay, that's something you have to think about. We're going to do that today. Furthermore, keeping in the back of our minds that when we go to write the domain for a composite function, we look at the original domains. I'm also going to show you a really cool trick to not have to graph the functions necessarily. So that'll be kind of exciting for today. I actually did it with you in the video just a little bit last night or the night before, depending on when you watched it. The one I showcased yesterday in the video was this negative 5x to the 1/2 power. And you might recall from previous lessons, we talked about how fractional exponents are actually radicals in disguise. So do you see there how I turned negative 5x to the 1/2 power into negative 5 times the square root of x? Everybody sees that? Okay, I have a question for you to make sure you're paying attention. My question is this. Why isn't the negative 5 underneath the radical with the x? Ooh, that's a hands. Ooh, who should I start with? Bailey. Very good. Negative 5 has its own exponent, right? Negative 5 is raised to the first power, so it doesn't get put underneath the radical. Nicely done, Bailey. Okay, so yesterday I said, hey, or whenever you watch the video, you could just go into your graphing calculator and see that the graph starts at 0 and then heads towards positive infinity. So that's how we got our domain there. However, this makes sense if you just look at the equation as well. Okay, I have another question for you. The square root of x, it's a pretty interesting little function. We actually can't take the square root of lots of numbers. There's certain numbers that we can't square root and get a real answer back out. Do you know what those numbers are? I'm going to ask the question again because you have to think a little bit here. When you look at the square root of x, what I'm saying is you can't take the square root of every number under the sun. we can't take the square root of certain numbers and get real answers back out. My question is, what type of numbers can we take the square root of? Good, Megan. Yeah, we can't take the square root of negative numbers, for sure. Is that clear? You guys remember that? Because you get imaginary solutions, right? And you can't plot those on the real number line. So Megan just said it. You can't take the square root of negative numbers. Well, look at that graph. There's nothing, not a thing over here at all. Not a thing. You can't take the square root of negative numbers. Those pieces for our function don't exist. So it's in this way that you could look at the equation and figure it out. Figure out the domain of the function. Do you see that? I think that's pretty cool. You could just look at the equation and decide like, oh, well, that's got a square root in it. I just need to make sure that whatever's underneath that square root is positive. You know, it's kind of nice. I guess I should say non-negative, huh? Because zero's lumped in there too. Get specific. What's up, Noah? Like right there. So I think this is kind of a cool trick, and we're going to explore it a little more today. You don't really need to graph the function in order to kind of figure out its domain. Pretty handy, especially if you don't have a calculator. So with that, we need to go back to that independent practice that you were just looking at, and we're going to talk about the domain. So in part A, and your homework assignment tonight too does say, you know, you have to read the directions carefully because your homework assignment for tonight, it'll say find f of g of x and then find its domain. So I'll be looking for your understanding of domain on your assignment for tonight. Don't skip that part. That would be bad. I need to make sure you practice with domain a little bit too. So if you take a look at part A, we have f of g of x equals 4 over 5x minus 2. What I'm trying to say to you today is that you could look at the equation and sort of make some generalizations about what the domain could be. Do you see this 5x minus 2? It's in the denominator of a fraction. So I'm going to jot this down, 5x minus 2. And I'm thinking about it a little bit. 5x minus 2, being in the bottom of the fraction, isn't allowed to equal a certain number. We're not allowed to divide by 0. Very good. Did you hear Noah? Yeah. We're not allowed to divide by 0. So 5x minus 2 is not allowed to equal 0. True story. So what I built for myself is a little equation that I could solve so easily. If you take a look at this particular problem, I could add 2 to both sides, divide both sides by 5, and what I come to notice out of that is that x is not allowed to equal 2/5. If you let x equal 2/5, you end up trying to take 4 and dividing it by 0. You can't do that. What's up, Anthony? That's a good question. I think the short answer is the denominator. But ultimately, you have to look at where the variable is because domain tells us possible values of x. So for this problem, my eyes go to the denominator because there's rules against what I can divide by and what I can't. But in general, when I write a description of domain, I'm looking for possible values of x. Right now, I've only identified what x can't be. So what can it be? Everything else. It's true. The domain for this function, and I'm going to show it to you on the graph. Oops. The domain for this function can be everything except 2/5. So we come from negative infinity to 2/5, and you see how there's a parentheses there? That means I can get really close to x equals 2/5, but I cannot touch it. And then after 2/5, I'm again going to get really close to it, but not touch it, and head towards positive infinity. What's so cool is that your graph will completely confirm this. This is a lot like 24 that Ms. Goldstein went over with you yesterday. It's in pieces. What's up? Yeah, go ahead, Luke, get it. What is it? in union with. That was, so you folks got robbed because you also had a fire drill. This poor class, I feel so bad for you guys. But you got this. It describes all the different ways you could write domain and range. Maybe go back and take a look at it when you get a sec. Yeah, Claire. Okay, so I'm going to show you, because ultimately you want to kind of piece together. We're still learning how to use an equation to write domain. I'm not even getting into like the deep end of the swimming pool with it. You still want to kind of bounce it off of what your calculator has to say. So I am going to show you that this holds water when it comes time to putting the equation in my calculator. So, do you see here, in my y equals screen, you don't have to do this. This is purely for your visual enjoyment. But I did put parentheses around my denominator. And do you see there how I have y equals 4 divided by 5x minus 2? I just entered in my function. And now I'm going to press graph. And what you see are these two pieces, right? You see this piece that comes up from negative infinity. It's really close to 0 here. Comes up from negative infinity, goes past the y-axis, and gets really, really close to this number that's close to 0 but doesn't touch it. And then right after that, it starts right here. This line still kind of close to the axis there and then heads towards positive infinity. So the ambiguous number that I'm sort of circling around is a number that's close to 0. We know, based on our algebra, that that number is 2/5. We know that that number is 2/5. How can we use our calculator to verify this? This is really cool. I like this. Okay, so what we're going to do is we're going to press second and calc. And I'm just verifying the fact that I have to exclude 2/5 from my domain. Check it out. So second calc, do you see that first option there? Value. That allows me to throw in whatever x value I want, and it'll spit the y value back out. But watch what happens to my poor little calculator when I enter in 2/5. It doesn't know what to do. Y equals blank. That's because there is no y value there. You can't put 2/5 in and hope to get a y value back out. So this is further confirmation for me that I've correctly excluded 2/5 from the domain of the function. Does that make sense? So it's pretty cool. I think that's cool, like how our graph kind of confirms what we found algebraically. I've always thought that that was really cool. Cool thing about algebra. Okay, part B. So let's see if you can do this. What number should I exclude from the domain of this function? Ooh, I heard it. It was over here, Kristen. It is 0. Very good. I have to exclude 0 from the domain of this function. Why did she say that? Yeah, very good. You can't divide by 0. Nobody can. So how do you write that? Because it's a rational function, it's going to have multiple pieces to it. It's going to look like that. It's going to come up from negative infinity, and you could, again, I think Claire was asking this earlier, you could put this in your calculator again. It's going to give you those two pieces. It's going to come up from negative infinity and take a break at 0. And then after 0, it starts up again and heads towards positive infinity.
Why for this one don't you have to solve that like?
Because I could just kind of mental math it. Like this here, x is not allowed to equal 0. It's not that x wasn't allowed to equal 0. The denominator can't be 0 in a fraction because we can't divide by 0. There's a difference between x not being allowed to be 0 and the denominator not being allowed to be 0. Claire, do you see the difference? We are never allowed to divide by 0, so it's the whole denominator can't equal 0. In this case, the whole denominator, Claire, was just x. But over here, in this case, the whole denominator, this guy right here, wasn't allowed to be 0, because that would mean I was dividing by 0 there. Yes? Oh, yeah. Like, think about all the other cases that you did on this paper last night. Good question. I'll answer that for you. Good question. Do you see how, okay, the quick answer to your question, do you see how there's more than one piece to this graph? It's defined in chunks. That means my domain can't be described with just one interval. I need chunks. So I have chunks in my domain. Yes, that's kind of what I'm trying to get to today. Really, we get these chunks when there's a big, it's called a rational function, a big fraction in the problem, if you will. There's going to be chunks. But a parabola, like if it were y equals x squared, well, that's negative infinity to positive infinity. Like, that doesn't have chunks, you know? Ultimately, you will have your calculator to produce a graph. I would also use that. We have to talk more about the domains of rational functions when we get to chapter 8. So I'm just introducing it now. All right, lastly, part C right there. Oh, okay, so this is the tricky one. So our function, our composition of functions produced x. Can anybody talk to me about what the equation y equals x looks like? Careful. It is a line. It's a slanted line. How so?
It's a 45-degree angle from x to y-axis.
Okay. Yeah, in both ways, right? So does it pass through anything special? It goes through the origin. Does everybody remember y equals x? You got a little mental picture right now? So you've graphed it in your head. You know, you didn't put it in your calculator. You produced a mental image of what y equals x looks like. Anybody not able to produce that image if I say it? Because it's super important for tomorrow too. Y equals x, we're all good? Okay. So with that, y equals x, you get this mental image. And Noah just said it passes through the origin. So back to the very beginning of my lesson today. I said that you must consider the original functions when you go to write the domain for the composition. The original function that this thing is built out of is 4 divided by x. So, is the origin allowed to be in the domain of this function? That is a really tough question. Really hard question. I need you to think about it. Let's take a vote maybe, just so I can see that everybody's at least thinking about the question. The question was, if this function, this composition of functions, produced the equation f of x equals x, but it's made out of this function here, 4 over x, is 0, 0 allowed to be a point on this curve? Megan, what do you think? Oh, okay, good. I wanted to take a vote too, but go ahead, Megan. Oh, okay, I can clarify that 2 seconds. So you know that this function was 4x to the negative first, right? You're not allowed to have negative exponents, Megan. So we use our upstairs downstairs rule. 4 is raised to the first power. And then if I want to make x to the negative first positive, move it to the bottom. So 4 over x. Make sense? Okay. So yeah, that's where that came from. Okay. So, who said, yeah, x can be 0 for this problem? Who said no? All right. And if you're unsure, you don't have to vote. That's great. Yeah. Okay, so if you said no, you're right. Okay, now why? Kristen wants to answer. Okay. No. Math never comes from because I said so. Let me be clear about that. Go ahead, Kristen, say it again. Because you can't divide by 0. Very good. If you let x equal 0, that's not in the domain of this function here. You can't take 4 and divide it by 0. You can't. So the domain of that function is also in pieces. But to go back to Danielle's question, your calculator will lie to you. If you type in the equation y equals x, you're actually just saying graph the line, y equals x. But what your calculator doesn't know is that you're actually trying to write the domain for a composite function, which is made of 2 other functions. Your calculator doesn't know that. Your calculator is only plotting what you tell it to. Y equals x, that's just a function. 0 equals 0, that's a point on that graph. But because we can't divide by 0, and our original function has x in the denominator, well, we can't let x equal 0 there. I hope that makes sense. This almost exact same problem repeats itself in number 33 on your assignment tonight. The 4 turns into a 3, and that is the only difference. So if you're having trouble, go back and use your notes. or watch this thing again, it'll be uploaded shortly after school today. But it'll talk, if you need another affirmation about why does 0 get excluded from this function, it's in your notes. Questions about that? All right, awesome. Next, we have one word problem and then we're done. So pretty short little lesson. I can address any of those domain type questions that you might have had last night as some of you went through the bookwork a little bit. Oh, and I got to talk about your homework from last night, the one that you just got back. Full disclosure, I went to the Gap over the holiday break. I had a really good coupon, and there was a really good sale, and it prompted me to write this word problem for you. So it's very candid. I love the shop. I love a great sale. This could help you. So we can apply composition of functions to like the next time you go shopping. So just to cut down to the bones of the problem here, I had a $10 off rewards coupon because I have a Gap credit card. And then they run like 40% off sales like often. So I go in and I was curious, I was like, oh, what's the cashier going to do? Is the 40% off going to come off first and then are they going to take my $10 off coupon? Or is she going to take the $10 off first and then take my 40% discount off? Because that matters. Do you know that? It's not the same, right? So what you're going to do right now is I just kind of explained that first paragraph to you. I said let X represent the original price of my item. Okay, you're going to do a couple of things for me. In the first part, I want you to write a function for me that describes my cost if I only use the $10 off coupon. That's A. In part B, I want you to write a different function that describes my cost if I only get 40% off. C and D have you writing some composition of functions that say, oh, how does the equation work out if they take the $10 off coupon first and then the 40%? And then in the next one it says if they take the 40% off first and then the $10 off. In part E, you're asked to analyze the difference between the two equations to tell me which one's better. So I'll go ahead and give you a couple minutes to think about that. Okay, so as I walk around, these first two functions went great. Throughout the course of today, there was general consensus among part A, f of x, x minus $10. Doesn't get more straightforward than that. I honestly ran into 3 different ways of representing the equation for part B today. The most popular one, the one that this class seems to be sticking with, is this guy right here. If it's a 40% off sale, I'm going to pay 60% of the item's cost. So, of in math class means multiply. If I'm going to pay for 60% of the item, that's 0.6 times x. So that's where that came from. Also, I think like Emily was using this approach. She thought about like, well, I'm going to pay x originally, and then I'm going to take off 40% of that cost. Again, you're just combining like terms. 1 minus 0.4 is 0.6. So that was good too. Now, the question I keep getting is, do I do g of f of x or f of g of x? Well, in part C, you're asked to take the $10 off first, which means f of x is the function that you're going to have to plug into g of x. Hence, you do g of f of x. So that should be your function for part C. And then part D, as I walked around, I saw 0.6x minus 10. So now, big conclusion, part E, which one's better? Part D, yeah, I'd save a couple more dollars that way. So for tonight, you do have bookwork. So make sure you take care of that, and we'll go over it in class tomorrow. And I'll talk about your bookwork that you just got back tomorrow as well. All right, that's it. Have a good night.